Okay, so I guess we can start now. There's quite some number of participants already here. So let's start with our ROS Workshop 2 application. In this workshop, we focus on more on the application, how we use ROS to control our robot. So later I'll be explaining you some concepts that are directly related to that. So this workshop is brought to you by MLDA EEE. Um, we are a student-run lab that focus on catering to students' interest in uh, deep learning, machine learning, AI, data analytics, and all the fields around it. And we work with we together we learn and teach other students to with workshops such as this one, and we have projects as well as events such as deep learning week that will be ongoing in the next week. And yeah, we're excited to have you here. So this particular workshop is a bit different because it's brought to you also by MLDA Robotics. MLDA Robotics is a new initiative from MLDA EEE. Basically, it's a subsidiary that deals mostly with robotics. Uh, our interest in is first of all to join in international competitions and train for it, and share our experience and knowledge throughout using workshops such as this one. So the competition we plan to join in the next year is called the RoboMaster University AI Challenge, and yeah, we even have our own junior training program now, which is very nice. So yeah, we are MLDA Robotics, and after this, I will also running this workshop together with UAVIONICS, NTU UAVIONIcs, and I think I'll let Junse explain your UAVIONIcs as the president itself. Junse, are you there?
Hello everyone. I'm Jinze from UAVIONICS Club. So basically, what we do for this club is that we are trying to create unmanned vehicles, either in the area of air, such as we have this autonomous drone, and then in the area of land, we have something like an autonomous vehicle, also something like a robot that Kent has shown just now. If you think that this is something that you might be interested in, just feel free to join us, and we'll be having more workshops and events in the coming semester. Yep, that's all from my side. Thank you.
Okay, thank you, Junse, for the short explanation. So this workshop is brought to you by MLD Robotics in collaboration with UAVIONICS Club. So let's start with the flow of today's workshop. First of all, I explain to you a review of the last workshop because it's very crucial that you understand the material from the last workshop. If you haven't watched it, this workshop might be somewhat difficult for you, but I'll try my best to explain it so that you can understand it. And we'll move on to ROS visualization concepts and tools. Last workshop, we visualize our topics using a terminal, which is not really just text and numbers, which is quite difficult, especially if we're working with 2D data or 3D data, for example. So in this workshop, we'll explain to you more about ROS visualization tools, which is RVIS. And then in the next part, I'll explain to you some concepts that are required in order for you to build your controller. And then we can start our hands-on session where I'll explain to you more about this, how we build a controller and demo you actually how to do it and let you try by yourself. So yeah, so last time we came up, had these questions in one of the slides. What is ROS? Well, ROS is not an OS, a normal OS, although the name is Robotic Operating System. It's not also a microcontroller or a microprocessor. It's actually a program that runs inside your OS or inside your microprocessor. In this case, inside your Raspberry, it's running on Ubuntu, and inside the Ubuntu, it's running ROS. So what is the function of ROS? ROS allows multiple programs that's usually related to robotics use to run simultaneously and communicate with each other. So in ROS, you can run multiple things such as a navigation node, wheels and an actuator node. You can also run image processing, localization. You can run nodes that allows your sensor to gather data, or you can even work with deep learning inside ROS. So to explain the concept of ROS, so imagine this ROS is running in your Ubuntu. You have a few codes in a sense running, and we call these codes nodes, NODs. So we have the code that's responsible for navigation running in a single node. This is one node. And then another code that sends out sensor data or allow the sensor to measure maybe range or something. Then we have the node that's responsible for running the actuators. So these nodes communicate with each other as we have the ROS master, or which is run typically by the command ROS core. So inside this ROS, with this, because there's the existence of this ROS master, our nodes can discover each other and communicate using what we call ROS topics. So these arrows represent ROS topics. In this case, the practical example would be, for example, if my sensor is an ultrasonic sensor, the ultrasonic sensor will send out the distance between the, of course, the robot, the sensor to a certain fixed point. Sorry, give me one second. A certain fixed point, and then I want to parse this range data and navigate my robot. For example, I want to tell it to keep moving forward. And this actual data will be translated in, say, a PWM signal in your motor, and it results in your wheels turning. So more or less, that's how ROS works. This allows it to be very modular, and I'll explain more about the benefits and why we use ROS in the next slides. So back to explaining an important concept, which is ROS topics and messages. So what is inside a ROS message, and what is a ROS topic? So ROS topic, like I mentioned before, is how the nodes communicate. So essentially, one node, like the sensor, publishes data, and the receiver subscribes to that data. And the ROS topic itself has a name in which it's identified and a message type that it carries. It could be range data, it could be a simple string, it could be a laser scan data or an image type data. And I'll explain to you these examples shortly, but just keep in mind that. And what's the difference between the ROS topic and the ROS message? Well, topic is the broadcast channel, the whole process of sending the data, in my understanding. And the ROS message itself is the singular message that's being sent out. So usually it contains a header, actual data content in the data format. So header would be timestamp, sequence number, and so on. Actual data content will be like the important stuff, the image data, for example, the pixel values of the image. And data format explains like what's the width and height of the image data, and so on. And so, yeah, it's more or less like that. Maybe better if I show you an example. I'm going to new share, and I'm going to share with you my whole desktop. So I have a terminal here, and I want to move to my workspace. And last workshop, we already do this. I'm not going to touch about the code too much. So later, I'll be explaining to you why we use all these commands. But essentially, let me just ensure everything is running smoothly, and we can launch our hopefully we can run our robot without issues. Yes, so now you can see my simulation. Here's my robot. So in this workshop, obviously if we use actual robots, then only 1/5 of you is actually gets to touch and work with the robots. So we came up with a simple solution. We use simulation. This is a simulated robot that's quite nice actually. And you'll later be controlling this on your own, running your simulation on your own. either by using a internet virtual machine called ConstructSim, or if you have installed ROS, then good for you. You can run it natively on your own computer. So back to the terminal. Our nodes are listed here. So we have the gazebo, we have the robot state publisher, which publishes the joints of the robots. I'm not going to explain it deeply, but I'm more interested in the ROS topics. So we have a lot of topics here. So let's take the example of command velocity. This particular node, I'll explain to you the theories behind it. But for now, I'll just ROS topic info /cmd_velocity. And then you see here that the subscriber is the simulation, which is this robot here, the simulation of the robot. And there's no publisher for it. So that's an example of a ROS topic. And if I want to run this robot, I will have to ROS run teleop. Just keyboard. I'll run a teleop node, which is a publisher of command velocity. And if I run this, then my robot will be receiving a forward command. I tap I, which translates to it. And if I subscribe to this velocity message, I'll see that, wait, it's not. Yeah, I'll see that it's receiving a signal to move forward, essentially. That's the idea. That's the idea. So this is the publisher. The robot itself is the subscriber in which it's moving. I think it's gone. So yeah, that's the simplest way to show you what is ROS topic. And yeah, I guess that's the bulk of the theory. Now, last example, last workshop, we also already explained the concept of ROS Note and Topic. This is through talker and listener. I think this is a even more simplified version of what I just explained. Our talker, the publisher, publishes these numbers, and the listener records these numbers. But in this case, they only record the number with a certain increment because the rate of the listener is slower than the rate of the talker. So simply put, say this is your sensor data. It's producing these numbers. Then this is maybe your navigation program, which requires this data to work. So that's how ROS works. The concept itself may not look as interesting as working with the actual hardware, but this is actually what's being used currently in the industry. If you go about and work with a robotics company, then you'll obviously be using ROS. So this is actually an example of usage of ROS. Now, this particular footage or photo of a footage is taken from the robot that I've shown you in this picture. So this drone has a camera, and based on its image data, it detects these visual markers, and then it sort of calculates its current position, 3D position, based on the location of the pixel coordinate of the markers. This is called ARUCO markers. So this is one example of ROS. So when UAVIONICS is building this drone, they don't need to build the ARUCO package by themselves. They use existing ARUCO package, and this is why we use ROS. So I'll explain more in the following slide. So what's so special about ROS? Here we have first of all, three benefits: open source, pre-built packages for components, hardware drivers, sensors, algorithm, navigation, ETs, and etc., and large community and widespread. These are actual benefits. In fact, these benefits wouldn't have existed if the community never existed. So why do a group of robotics enthusiasts suddenly joins together and build ROS? Well, it's really to do these things, to make everything modular, to streamline and standard that format of workflow in robotics, and allow and the third benefit, which is a very good one actually, essentially allows communications between multiple robots. So that's the idea of why we use ROS. So allow me to explain this example using this particular slide. So when working with robot parts, we have different brands of stereo cameras, different brand of lidars, but essentially they produce sort of similar data, right? Maybe the width and height, the field of view is a bit different. Maybe the angle of the LiDAR starts from 0 to 6.28, while this one starts from minus 3.14 to 3.14. Maybe that's the case. Who knows? I don't actually own a lot of these sensors. They are quite expensive. But essentially, all this data boils down to sort of the same type of data. An image data, for example, consists of an RGB, 3 channels, in which it's 3 different matrix of pixel values. One corresponds to the red color, one corresponds to the green color, and one corresponds to the blue color. Combining these 3 values, we get our image. But a problem arises when you see this. There's a countless number of ways to represent this data. For example, I can represent all this array into all this 4 times 4 matrix into a 16 times 1 matrix or 1 times 16 matrix. I can represent this data in a BGR format instead of an RGB format. So this would create confusion. And what would happen if I write a program specific for my camera, another person will need to rewrite the whole program and change it to make it work with his camera. So rather than that, the alternative is ROS. So you see here the type of message there is image sensor messages / image message. So this essentially explains allows you to standardize your data into the format that ROS uses. And although your data format itself is different, maybe you have different size of camera. For example, one creates an image of 640 times 480, the other creates 720 times 480, right? So using this data here, a programmer of a certain algorithm can ensure that his program works with any type of camera that follows these sensor messages, that outputs the sensor messages listed here. So this is the same with laser scan data, in which we will be using today in our hands-on exercise. So here in our laser data, we have angle min and angle max. This explains the minimum angle, like I've explained before. So essentially, if I have to visualize laser data, this is our robot in the middle. The LiDAR constantly rotates and takes the distance of the point, takes the distance between itself and the nearest obstacle. So say the robot is facing this way. Then the data would be all these data points. So one distance, an array of distances. So this is the first distance, this is the second, third, fourth, and so on, rotating until the whole laser is received. Actually, you can see the configuration I made here. So that's the concept of angle min and angle max. Angle min is the starting angle, and angle max is the ending angle, if I have to explain so crudely. So you start with angle min. Let's say your minimum angle is minus 3.14, then it's facing the negative direction. And it pokes 1. until you hit the angle max. And then you have the angle increment, in which you have the minimum first, then you increment until you hit the maximum angle. That's the concept. So for example, if your increment is 1 degree, then you first will go minus 180 degree, minus 179, minus 178, and so on. And then you have your time increment, which is the time difference, where because the LiDAR does not shoots laser in all direction all the time. Instead, it actually fires one laser, finds the distance, and rotates and fires again. So there's this time increment, and then the time between scans, or the total period of the rotation of the LiDAR. Then you have the range minimum and range maximum, which is the minimum value of this. So for example, the LiDAR can only detect stuff on the range of 0.1 meter up to 10 meters. So that would be the range minimum and range maximum. And finally, you have the ranges itself, which is the data, the points distance itself. And then you have the intensity, which I'm not going to explain because this is a bit more different, and usually it's not used as much as the other data. So what would happen if we do this? What's the benefit of standardizing everything? Well, take an example of AMCL. AMCL uses complex map. As an undergrad, I find it difficult to code it myself. I would need to spend some time, like a whole week dedicated just to properly code a fully functioning AMCL program that's up to par with the existing ones. But I don't have to do that. In fact, these nodes is made to accept the exact same laser scan messages, irregardless of your brand of LiDAR, as long as it supports ROS, of course. It takes in the transform, which is the distance between the center of your robot to the LiDAR. Then it takes in your initial pose relative to the world. This can be GPS data, it can be anything, really. And it takes in the map, occupancy grid. By simply providing this program with all four, you get the position. So instead of rebuilding your whole program, everything you rebuild by yourself, ROS essentially allows the community to skip all that and use others' existing program. So later on, when you're working with ROS further along the way, you'll be encountering many packages, and chances are you just need to use these packages with minor modifications, which is really one benefit of ROS. When you're working with robotics that deals with ROS, you don't have to tweak around and make your own program. But yeah, you just have to use the existing repo. It's a very powerful benefit. So summarize why we use ROS. It's this meme right here. Some smart dude out there who program Kalman filters, who program complex navigation or path planning. And this is me, who simply uses all those stuff they provided and maybe add a little bit of my own. But that's essentially why we use ROS. So our hands-on will exercise today will be to run this turtle bot. Oops, I think I already have a terminal for that. So, oops, let me just kill this and rerun. Let me just minimize that. So you see this pillar right here. We want our robot to hit that pillar, to drive and hit the pillar. So for example, I'm going to speed up my robot. I'm going to turn it that direction, and I want it to accelerate and hit the pillar. Oh, it's quite difficult to control. Yeah, but you get the idea. Yeah, it's spinning around quite a lot. But yeah, you get the idea. I want to control my robot to hit the pillar. So how do we tell the pillar, right? How do we know where to hit the pillar from? we're going to use the laser scan data. But before we discuss more about the laser scan data and its visualization, I'm going to have to explain to you how we control our robot first. So essentially, a lot of robots that support ROS will subscribe to the topic called the command velocity. And this command velocity will be a message of type geometry/twist. So what is this geometry/twist message? It's, in a sense, it's a message containing two different vectors, one linear, one called linear, and one called angular. And this linear is a vector type message, which contains X, Y, and Z data. So with linear, it's pretty self-explanatory. Your X always points to the front of your robot in the convention. Then your Y will be to the left and Z will be to the up. So when we're working with our robot, we'll only be using the X and Y linear value because our robot cannot fly. And for the angular data, we can see here it uses the right-hand rule. If you stick your thumb to the direction of the right-hand thumb to the direction of the vector, then you get the rotation axis of the vector, the direction. So Z corresponds to the yaw, which is the only angular velocity that we can use. The twist will accept anyway X, Y, and Z. But when the actual guy who develops the robot, built the robot, he will ignore this Z value, for example, in the linear case, and only parse the X and Y data and translate it into motor voltage, for example, to actually get it to output something. So that's the first concept of the command velocity. Now we move to the next concept. When we're working with LiDAR data, for example, it wouldn't make sense for me to to subscribe to the laser data like normal, because the data will look like this, right? Only some useful data, the rest will be infinite, and this will be spamming. So we need a way to visualize it, of course. So ROS has a tool called Harvest. And let me demonstrate it. All I have to do to run it is type Harvest. And this is Harvest. And here we have the first option that we're going to need to work with. It's the global option. This fixed frame refers to one frame that you declare as the anchor point of all the visualization you have here. So we don't have a map because I didn't load a map, but we have our robot odometry that we can use as the anchor point for now. So this fixes the global status. And later on, when you're working with your own RVs, you need to do this. So remember, change the fixed frame from map to ODOM. Then the next step you need to do is to add. So this add thing adds a visualization tool for all this particular topic. Let's start first with our robot model. There we can see our robot. And then the rest of the stuff, this is a pretty intuitive tool. The rest of the stuff, you can just click by topic. And for example, if you want to see the image of the camera in the robot, then you can click on image right here. And you can see there's nothing there, but if I add something to the front of the robot, that should be visible from here. Then I want to visualize my laser scan data. So I just go to add, like before, by topic, laser scan. And I have the laser scan here. I can also modify it. Maybe I don't like this to be flat squares. I want to change this to circles. There's also spheres. That's also possible. I want to change the size. So it's really a visualization tool that later will help you a lot in working with your robot. So that's the second concept that I explained to you now. And for now, I'm going to kill my RVs because it's causing my computer to lag, coupled with the gazebo and the screen sharing. So I'm going to kill that because the next concept I want to explain to you is a controller called PID. So if you're from EEE year 3 and you take control engineering, then you will understand this concept already. And I'm not sure for other faculties, or if you're a postgrad or someone from the professional field, you might have encountered this particular concept already. I'm not going to go into a very theoretical explanation of this PID concept, but later on we'll use this to control our robot and get it to run in the correct direction. So essentially, how do I explain this PID? So if we have a it's a control mechanism that uses feedback. That's how I define the controller. But explaining it is a bit more tricky for me. Imagine you have a DC motor. It's called a system. I'm going to call this DC motor my system. It accepts voltage as input. And like any DC motor, if you give it voltage, it will start to spin with a certain RPM. So it outputs speed, measured speed here. Imagine I put 5 volts. It will rotate 100 RPM, for example, with no load. But then I add a wheel and I let it run on a surface. Of course, it wouldn't run with the exact 100 RPM if I use the same voltage mark. So we need a method in which we, based on the error, we get our reference. We might be able to control our increase our voltage input and make it the correct value that allows it to turn 100 RPM. So here we start with a reference and an output. Our plant produces our output, and we want the output to be equal to this reference. So, so essentially what I do is subtract the reference by the output, and I will have the error. And I want to correct my controller input, the input to my plant, based on this error, so that it produces the correct value. So in this concept, PID, we multiply the error with a constant called Kp, which is the proportional constant. Then we multiply the integral of the error by Ki, which is the integral constant, and we multiply the derivative of the error with a Kd, and then we add all these 3 values together, and we get our input towards the system. I'm going to explain why we use these 3 different constants shortly, but here's one example. So we have a P controller. By itself, it creates an output that oscillates, overshoots, but it reaches a certain steady enough state. And in comparison, when I use the PID, my response is very fast and very smooth. So the idea is I want to control my robot or control my system such that it has a very, very smooth response using this PID controller, rather than just telling it to turn left if the object is in your left. That's not really a good way to do it, right? So I'm going to explain this concept of why we use PID using a very...
I'm going to continue with the introduction.
I'm sorry? I'm not sure. Can you put that in the chat? If was there a question or something? Never mind. Okay. So yeah. So imagine you have a car, and in this car, there's a sensor that tells the distance between this pole and this car. Let's just say the distance between this pole and the front of the car. So imagine I have an error, right? the sensor tells the error of the distance. So when I saw that there's an error, simply I multiply that by a certain constant and consider that as my speed input. So imagine this, this is an electric car. Instead of acceleration, we have speed input. Our input is already a velocity. So I tell my car to move forward with a certain speed based on the error. When I reach this point, I'm telling my car to stop. But when I give the command to stop, the car still rolls. This is called overshoot. So what will happen with a PID controller? Like you see in this oscillation, the car will start to move forward. Oh, and then correct it again, move backward, forward, backward. So that's PID controller. Now, how do I soften that? We use something called the D constant. So imagine your car is accelerating. It's increasing speed, which means you want your car to increase the speed, right? So when you're accelerating, you want your car to increase its speed as quickly as possible. And to the contrary, when you're decelerating, when you're nearing the pole, you want your car to decrease the speed as quickly as possible so it doesn't overshoot. And what constant happen to be positive when you're accelerating and negative when you're decelerating? The derivative. So by adding the error derivative multiplied by a certain constant, I increase the speed of my response and decrease the overshoot. That's the concept of PD. PD controller, proportional and derivative controller. And for the last example, the integral controller, why do you use PI controller? Imagine we have the car and we have a certain amount of error. And this pole, similar to the car, is also moving at a certain constant speed, say. Then at one point, there will be a value of distance that corresponds to the same speed as the pole. What will happen is the pole will keep moving and the car will have a steady state error. It cannot catch up with the pole. It will just have that gap, but it does not fall behind the pole also. So how to fix that? We sum the error so the car slowly increases in speed and overtake the pole. So that's the concept of PID, explained in a nutshell. So when working with your PID, you may need to use this particular table. So KP increases your increasing your KP decreases your rest time and overshoot. So if I increase the KP value, this is like making the spring stronger between this pole and your car. So I'll accelerate much faster, but I overshoot more. And it has small change to the settling time, which is the time it takes for the car to oscillate less and less until it reaches a steady state. And it will decrease your steady state error. So yeah, but by having a higher KP, of course, the speed that corresponds to the same speed will be the gap that corresponds to the same speed as the pole will be much less. So that's increasing your KP. Increasing your KI will decrease the rise time, same as before. By accumulating all the errors, you propel yourself forward, but it will increase overshoot, increase the settling time as you might oscillate more, but you will reduce the steady state error greatly. Then with KD, you will not help the rise time by that much, because KD is only helping you accelerate, but also helping you decelerate faster. So your car doesn't zooms really fast, but instead it really slows down here. But at the same time, it increases your acceleration also. So instead of slow acceleration, it goes very much quicker. So it does small change to the rest time, all in all, but it decreases your overshoot by a lot. Like I explained, it decelerates quicker and accelerates faster, decrease your settling time, and thus almost no change to your steady state error. That's the concept of how you tune your PID parameters. So when we actually want to create a PID value, we start with a reasonable P value. Then we tune the other two values. We start to increase the P value and see if we is it oscillating too much, then we give it a KD value. And if it has a steady state error, then we give it a KI value. And yeah, we play around with this value. There's some methods that are used normally in control systems engineering that are more theoretical in sense. There's Ziegler-Nichols method for tuning. For systems, you can use system identification tools in MATLAB, in which you give it a frequency-based input and do a frequency sweep to tell the response of your system in order to tune your PID properly. But for our case in high-level controller, it's actually been a debate on how to properly tune your PID. But the most common answer I see when I'm working with PID or when I'm looking with internet is just using this method. So you tune it slowly with this. If you're keen to learn more about controllers, you can take up the courses in NTU corresponding to control systems. I'm not sure of the course outside EEE because I'm from EEE. The course would be 3011 and 4207 for me. EE for 3011 and EE for 207. EE 3011 teaches the theory of controller, and EE4207 teach its implementation and how you design a controller typically. So, and one of the controllers that will be discussed is the PID parameter. So yeah, or if you're interested more in the high level side of PID, for example, for our navigation case, instead of the motor, it's often less possible to determine your system response if it's like this. So usually you use some, there's one method that I'm aware of, which we call it, I think the name is Twiddle or something. So essentially, they use some sort of machine learning to iterate to every possible values. So you start with a value of KP, increase the KP, see if it's better response. For example, if your parameter for your response is how quick you hit the pole, how quick you reach the goal, for example. So they sort of increase the KP, see if it does better. Then if it does better, then they keep the increase, or they decrease the KP and see if it does better, then they keep the decrease of the KP. Otherwise, it will keep the KP in the same value, but increase it by a smaller amount and repeat all the time with the P and I and D. So it's more of a machine learning, like similar to machine learning training, the method. This method is, if I'm not mistaken, prone to local minima. If you want to learn more, I think the course is taught by Sebastian Thurn. Yeah, you can just look for Twiddle PID YouTube. But yeah, that's the idea of controllers, and yeah, that's the concept. So PID has a lot of uses. Typically, you don't you're not stuck with one PID loop. You're stuck with multiple. And this is an example of one of the projects that uses PID. This is done by us from MLD Robotics. So we have a face tracking drone project. In this particular case, I propel the drone to move sideways to the right, but I want it to rotate properly to center to my nose. So this is an example of PID. So right here, I move the robot simply to the right using by putting linear velocity X on the Y direction, positive on the negative Y direction, then here the error grows bigger. So my controller kicks in and tries to close the gap. So that's, I guess, is one of the example of PID. And when you're working with cases like this, often you're not going to have one PID loop. Often you have multiple behavior tree and corresponding PID loops to work with it. For example, when I'm looking at this direction, compared to when I'm right here in this position, there will be different PID loops. So that's how I control my drone at that time. This particular drone is not using ROS, but your example later will be using ROS. So yeah, that's also one of the concepts that I need to explain. Then another thing I want to explain to you is called ROS param. So if you're familiar with C++, which we will be using today for coding, each time you change something in C++, it doesn't matter if you just change a line or change small variables, you need to recompile it because C++ runs with an executable. So the ROS guys noticed this and they built this feature called ROSmara, which essentially allows your code to take in the parameters like this example. For example, I'm reading the parameters using this getParam function. And so instead of, so what happens when I do this is instead of each time, for example, if I want to tune my KP value, I don't need to rebuild my controller, but instead I'm just going to read it from my ROS param config file or .yaml file. So how do we go about with working with this config file? Typically in our package, let me check with this. I'm going to pick into my source folder and pick into my TurtleBot3 controller folder. And I have a package. This is explained in the previous workshop. So in this package, normally I would create a new folder called config. And inside this config will be a .yaml file. So when working with the config file, I need to tell my node where to find the config file in the ROS launch. Later, I'll show this. I'll code this with you. And after telling it to load, then I will create a function. Oh, when initializing my program, in this case, I use OOP. So when initializing my class, I would define default parameters that would be the value of the variables when the ROS param reading fails. But anyways, what we do usually is create a function called read parameters. And this read parameters will run this particular function in which I declare a Boolean success and set its value to true. And I'll run this get param function, which is used to get the parameters. And this has two arguments. First of all is I'd say the directory. So here you will later write TurtleBot3 underscore controller slash scan subscriber topic name, which corresponds to this. And then this get param function method returns a Boolean value, true or false, when it succeeds in getting the param. So the second argument is the variable that you want to feed the parameter value into. So when it succeeds, it returns true. When it fails, it returns false. So I want to read my parameters. One by one. And if everything succeeds, I will return true. If one of them false, I want to return false. And if this read parameters is false, I would push to my, I would write into my terminal that I could not read parameters and request the shutdown of ROS. So there's two methods I did put here, which is kind of unnecessary, but okay. First of all is putting the default values. So in case the read param fails, it takes in the default value. Second of all is to kill it. Why do we kill it? Imagine you put your KP controller and it fails to read your KP. Then your robot spins around. Might be somewhat dangerous. So when it fails to get the parameters, you might want to shut down your robot or shut down the whole ROS thing. So yeah, I believe that's all the concept that I have to explain for in today's workshop, because this is more of an application workshop. So yeah, in this particular application workshop, I'll demo you and you can try this by yourself, follow along, how to subscribe to laser scan messages, how to parse the data and take out only the useful information that we need, and how to build a PID controller to control your robot to hit the pillar. Very simple case. So yeah, all those concepts I explained to you will be used today. So how do you go about and following me with coding? So I give you two choices. The first one is you git clone if you have ROS installed. If you have ROS already installed, you can git clone from the link I give you. So if you're a native installation ROS, then you might already know how to work with ROS. So all you have to do is clone this repository. So let me just show you. Maybe I'll do this. So I'll have my workspace and I create a certain folder here. And this folder normally will be empty. And then I create an SRC folder. And the contents of my GitHub all goes into this folder, inside the SRC folder. Then I'll return to the Turtlebot or the workspace name, and I'll catkin make or catkin build. So if you already remember, that's how you do it. So say I already clone, or if you don't know git clone, you can download this zip and extract and copy the contents into the folder like this, like this. Then you can return to your terminal, and then you type catkin build or catkin underscore make. Both works in this case. And this particular program or stack, Turtlebot stack, does not require any dependency because I've already included all the dependency. And when you build or make this particular package stack, you don't really need to do anything. Like install any other sort of dependency. So that's the first option if you have ROS fully installed. And by the way, this works in ROS Melodic and Mitic. I have never tested for Kinetic, but I assume it is. It does work anyways because the package does not have anything that's sort of incompatible from there. But if you particularly have not yet installed ROS, because you maybe want to learn more before installing some dual booting your computer, for example, or installing WSL on your Windows, or creating a 5 gigabytes Docker to work with your ROS in your Mac, then you can use ConstructSim also, which is the same emulator that we use. So I'll paste this link in the chat. So you go there, and I'll show you exactly what I'm doing. I'm just going to log in. So you need to make an account if you haven't worked with ConstructSim before. And then you search MLDA underscore ROS, and you find MLDA ROS Workshop 2. Try to find the one under my name, which is Ken Howard 20, similar to my GitHub. So if you find the MLDA ROS Workshop 2, you click on it, you fork it, and it will appear in your ROS checks, in my ROS checks here. And yeah, you can find the one with my name in it. And then you click it and you run it. This will create a virtual environment in your browser, which is practically similar to your Ubuntu, and with this you can walk around and play with your play with the ROS inside. So something that you need to know, this takes quite a while to load. So first of all, we open the code editor. I believe this is it. I've put everything inside Catkin Workspace SRC. And the package that you want to concern yourself with will only be this TurtleBot controller. The rest you leave alone. This is just the requirements for the workshop. And later you'll be concerned with only touching this TurtleBot 3 controller launch, TurtleBot 3 controller CPP, and TurtleBot 3 controller.hpp. So yeah, I'm not sure why this is the case, but for the autocorrect in this thing does not work, but this code is working fine. So if you follow along and type everything I type, or you try by yourself with your C++ skills, for example, then it should by right work. And when finished coding, like last time, you can cd turtlebot cd to your Catkin workspace as and like Catkin build like normal. Oops, I use Catkin make here. So to use Catkin underscore make, and it will build/make your executable files properly. So this will function exactly like the corresponding native installation. The only difference is when you launch. So to launch our controller node, just remember to type turtlebot ROS launch turtlebot 3 underscore controller, then just tap or type T and tap. And you hit enter here. When working with, also one more thing you need to do is type this command, turtlebot 3 underscore model equals to waffle. This essentially tells what model of turtlebot you want to use in your simulation. In this case, we want to use waffle, and then we can launch the simulation in our ConstructSim. And when you open the gazebo simulation, it will not directly show up. So you need to press here, open gazebo, and it will load your gazebo, similar to the native one. Then when you need to use RVis, the visualization tools, it will not directly pop up when you type it. All you need to do is click in your graphical tools, and it will show RVis. So that's the simulator. Quite tedious to work with, but it works. I'm not going to use this. I'm just going to kill this. Oops. Instead, I'm just going to use my standard PS Code and native installation. So get param function returns boolean. You want to check the boolean if it's true. So or maybe I explain to you the whole code. So when coding C++, the good coding practice is to separate it into 3 separate files. Your HPP, inside your include/package name, your node, which is your main loop in a sense, and your CPP file, which explains the contents of your class. So we use object OOP here. So first of all, I want to declare my class in the .hpp file. I name the class turtlebot 3 controller, and I create the public and inside the public I create the constructor and destructor. Then I create my functions, which we all need today, which is the read parameter, scan callback, and publish velocity. So inside your HPP, you only declare stuff. Then I create my publishers, my variables here. Then your main node is just a main loop. It's like if name equals to main in Python. And this is where you put all the I guess the function, the methods of the class. So here I have my destructor, a constructor, and I wanted to have these default parameters or arguments. And when I don't put out any in my main loop, if I don't write any arguments, then it will just create this based on this default value. Create these variables based on the default values. And yeah, this variables is also declared in my HPP. So to keep note, so when you're building something, you might want to declare it first. When you write a new variable, you want to declare it first. Then first things, when I run my constructor, I want to read parameters, run the read parameters like I've explained in the slides. Then I want to initialize my subscriber, my laser scan subscriber. So we're working with laser scan messages. So we initialize the subscriber, and then we initialize the publisher of the velocity. So this is already explained in our last workshop. So subscribe, you put the topic, the queue size, then you put the callback function, and yeah, put this because this is for OB. And then working with file publisher, you advertise the message type and the topic you want to put out. That's pretty much the short explanation. So here you have the read parameters function. I explained to you already, so I'm just going to do this to make this quicker because we're quite behind schedule. And yeah, oops, it's starting to lag. There we go. So check all the variable. If it's getting okay already, later on you need to type this one by one. But yeah, I'll leave that to you in your exercise. If you don't want to use parameters, then you can declare this in your hard code it in your constructor. Like you can put the default values here and not run the get param function at all. That's up to you. But later when you do tuning your PID, you'll need to catkin make, catkin build every time you change the value of the PID instead of working with the config.yaml file. So laser scan callback. The function is the callback function. So each time we receive a laser scan message, we call the callback. And we want the callback to receive the laser scan message itself or a pointer to the laser scan message. And we want to parse this message. So give me 1 second. So first of all, when working with this, how do we, so let me just visualize this for you. In our world, I technically cheated. There's only one pillar. So, of course, if we show RVs, if I tap RVs here, change the map to an odometry, add my laser scan data. Nope, it's not really seen here. I'm not sure why. But yeah, anyway, we put something here. It's not showing anything. Oh wait, I never write the topic, is it? Yes, slash can. It's not receiving anything. Yeah. I don't know what happened there, but it should be working fine, I suppose. You see the lines here. So if there's only one box here, then of course if we detect something, it's that thing. If there's nothing else there. So what I do simply is for my code, I plan to take in the minimum distance. and just, for example, I'm facing this direction now, and based on my laser scan, I want to take the angle of the minimum distance, which is this angle right here. So we start, in my case, I think I started with minus 3.14. So the error angle will be this angle here. This is 0. This is the error angle. And I'll use this as the error in my PID controller and tell my, multiply the error by the kp, and then multiply its derivative by kd, and multiply its sum by ki. And that output is the velocity twist message angular z value, which will in turn turn the robot. And then how do I make this robot collide with my object? Is I just simply propel it forward, and it will adjust its course to hit the pillar due to the error. So that's the idea of the code. So let me just quickly code that. Let's start with float angle. This is the float that I want to get the value of. So I already write down the C++11 method here, but I'll explain the C++98 method because it's more friendly to non-C++ users anyway. So float minimum, I want the minimum distance, right? So I create a new float minimum, which at this moment will be message, which is our ranges max. So this is the longest possible value, which I hard code, if I'm not mistaken, to 50 or something inside the robot description code. So I want to iterate, so I for loop for I equals to 0, I smaller than the messages dot ranges. Oh wait, I need to use range. Oh right, I need to declare here integer ranges dot size, and this is a method. So this will so for I equals to 0 until I smaller than the ranges dot size, the size of the ranges or the amounts of distant data inside my laser scan message. And each time we do that, I want to increase my I. So as simple as that. Tap and we do this. And then if the messages slash ranges, this is an array I. Oh wait, if the minimum is larger than the messages dot ranges I, then I want, wait, I make this easier to see. Then I want to make the current ranges, current minimum to be my message I. This, however, does not return me my angle, right? So simply angle, if we check the definition of the message itself, I think it's right here. So we have the angle increment and the angle minimum. To calculate the error angle, we simply make use of that information, and we add the angle min, messages angle min added by I multiplied by the angle messages angle increment. That's how we get the angle. And then I want to call my publish velocity function. So I call this publish velocity, and I wanted to accept my float. Oh, I don't have to declare it here, angle. So call the publish velocity. And of course, if I want to accept a argument inside here, I need to type it in the function. But again, this is not the part where you define your code. Instead, you would define your method here. So I need to add here as well, float angle. And that should correct all my errors. How do I get the... Then from here, I want to tell my... I want to create a variable, which is the velocity message, which is a geometry twist object. So first of all, I want to tell my robot to propel forward. So I give it a x velocity, which I've already added here. Then I want the angular z to be based on the error, which means angle multiplied by kp. This is proportional controller. Then I want to add derivative. How do I do that? Angle. I want so essentially it will be the difference multiplied by kd, right? But this difference can be denoted by angle minus pref angle. And there's no variable called pref angle yet. So I need to define it in my HPP, like so. And it should correct my error. Moving on, we want the I controller part. So ki angular multiplied by the sum of the error angle. And again, I need to declare this. Where's my HPP? That should fix the error temporarily. And a semicolon, C++. Then I want to publish this. So what is my publisher name? Vel publisher dot publish my velocity message. Semicolon. That's essentially the code. So, oh wait, we forget one part. We need to calculate the pref angle and the sum error angle. How do we do that? For previous angle, it's quite clear. After we use the angle, we save it to a pref angle, post angle. So the next time this loop runs, this callback is called, it has the value of pref angle, which is defined in my class, so I can use it anywhere inside my class, whether it's in this method or this callback method. So that's the first thing. And then the sum error angle is just sum error angle plus equals angle. But this will pose a problem, actually. If you do this, imagine your error piles up. This will create your robot to be unstable and it will spin around. So not the optimal solution. So we need to deal with the integral wind up. So how do we do that? Deal with it usually is if the angle were to, if there will be a zero crossing in our error angle. So if pref angle times angle smaller than zero, denoting a zero crossing, sum error angle equals 0. Else, oops. Else, sum error angle. Wait, I already have that typed down. Equals plus equals angle. So essentially, that's the whole code. Now to add that in my, let's start with a small value of kp. and nothing else. And then I want to launch it, right? So ending to my launch file, I want to launch the controller node, which is of, we can give it a name first, and we call this turtlebot 3_controller. Then we declare which package it's from. The name of the package is right here, turtlebot 3_controller. And finally, we need to tell it where which program it is, which is our turtlebot 3_controller. Where do I get this type? It's you normally write it in your CMake list. So add executable, and the executable is the project name, which is written right in your package XML, also written, and I think it's also written somewhere up here in the CMake list. Oh, here. So that's where you get the launch file. Then I want to ROS parameter. Remember, we want to use the config file. So we tell it that the file is located in turtlebot 3_controller package /config. Oops. /config.yaml. And give it the command load. Close it. Then I close the node. To better visualize things, I want to run my RVis. So how do I run my RVis? Using a launch file. You type here name equals to RVis. Oops. Give it a name first, which in our case will be just simply RVis. Make things simple. You put the package name. The package of RVis is from RVis also, and the type is also RVis. Then you pass args. This is a method. Wait, let me check if this is the proper definition. Yes, you give it. This is how. So essentially, when you run RVis here, you can like save the config, and load it. So each time you run the RVis, you don't need to like put in everything, like add all the robot models and stuff. So how you do that is I've created my own RVis file here, which you will also have. So this is not coded at all. You use the GUI to create this. And how do I load that config for RVis configs? If I'm not mistaken, there's a way to load it here also manually, but you can also do it with your launch file by looking for the RVis file, which is in my turtlebot 3 controller package inside the RVis folder, and I called it waffle.rvis. So if I save the config also, and kill my RVis, kill my gazebo. This is already killed. Actually, don't need this. I don't need this terminal anymore, so I'll wait for my gazebo to finish stopping. Now since I modified the catkin file, for me I use catkin build, but you can use catkin make. You modified the C file, you always need to do catkin make. Now I want to ROS launch. I've already made this. Actually, you need to do one more thing, which I've already did earlier, which is run this command inside your catkin workspace folder, or in my case, I name my catkin workspace the robot. So after that, I want to ROS launch Is there something? Turtlebot 3_controller and mismatch syntax line 8 column 2 launch XML syntax. Oh, I missed something here. Oh, there you go. Starting go back again. Let me launch. And my robot should be trying to crash the pillar. And I didn't tune my PID here. So it's going to be the most pathetic turning. Maybe you want to make it faster, up to you. You can tune it by yourself and test it. Now we're going to separate into breakout rooms where you'll get to discuss more with your TA if you have any questions. And you can continue coding there. And yeah, hopefully you can learn some stuff. So in this particular exercise, you don't have to replicate exactly as what I did here. You can be creative regarding your controller. For example, instead of telling it to move with a constant speed, you can use also a PID based on the distance. You can fit this with another float distance. And based on this distance, you use a P controller or whatever controller you want to use to control your to tell the robot to move forward. So yeah, be creative with it. You can also just use angle times KP angular and leave the rest to be 0 if you want to be lazy about it. And yeah, this will probably leave a path where your robot does not moves forward in the wrong direction. And as the error gets bigger, it starts to turn faster. One way you can deal with that is multiply this error by the distance. Up to you. There's many solutions to this problem. And yeah, you can try around, play with it, and hopefully you learn something today. So we're separating into breakout rooms where in each of your breakout room, there will be a TA, and yeah, you can play around with it. So yeah, Nelson, can you start?
Okay. Hello. Okay.
Okay, I can hear you.
Okay. So yeah, I guess that's all that I can teach you for now. Concluding note. Good question that was asked in my breakout room is that is PID the best? Is PID the best option? Well, very debatable. We don't know what the best option right now. There's reinforcement learning that's somewhat strong, and PID isn't a method that produce the best output per se, because the best output is not defined anyway. There's no sort of parameters. We can tune the PID as such that it makes our response overshoot higher, but reach our target quicker, or vice versa. We want it to be a very stable, smooth response. So it's more of a trade-off game. And PID is just one of the methods to achieve that. And one of the strongest things they're looking into right now is reinforcement learning for control systems. But there will be another 2-hour lecture if you explain. So we're not going to go there. But instead, we're going to go here. So if you want to study more, again, my only reference is to go to ROS Wiki. It's the best sort of guide you can go. It's the documentation. And yeah, if you're interested in learning to use ROS more, please feel free to use my simulator, or not my simulator, the simulator I've distributed for you. And yeah, play around with it and install ROS maybe if you are right now are playing around in ConstructSim. The next workshop, actually, I will show you. We have a third workshop, which I will show my whole desktop. So instead of one object, I'll add more objects. So, and instead of chasing
pillars, you will be chasing another robot. So of course, we need a different sort of method to do this, right? We cannot just use the LiDAR trick. There's other objects. If I put a ball here, it'll be confused. It'll follow this ball. So in the next workshop, we will be using object detection based on the camera image, which you can see here. I think I load the RVs improperly, some error there. So based on the camera image, we will apply object detection, and hopefully we will be able to control our robot to chase another robot. And we'll be using the same PID concept, but of course the difference here is we'll be implementing object detection directly in our simulator inside ROS. So that's an interesting concept that if you're interested to learn, you can come to our next workshop. Plan to be on the next week, but we'll see depending on that. This workshop, we will post the recording as soon as we finished editing it in YouTube. And yeah, you can watch if you want to learn something, if you want to refresh your memory on something you learned from here. And yeah. Oh, one more thing to mention. So in the next workshop, I recommend you install ROS Noetic in at least you need a WSL or WSL2 Docker or native Ubuntu installation, or yeah, Docker in Mac also possible. So I give you these options. If you use ConstructSim, it's not going to work because object detection obviously requires a GPU even to run the model. And if you run it in CPU inside ConstructSim, it's just too slow to run. So if you're interested in learning more and actually work with robotics more, so I recommend you really install ROS natively. Best option is to dual boot your Windows laptop and run install natively. That's the best option. If you want to work as a professional robotics engineer, that's the most convenient way to do this. So yeah, I guess that's all. And yeah, of course, the benefit of installing in natively or using Docker is that you can actually work with actual hardware. So today you see us control a robot using the command velocity command, right? Command velocity topic. In actuality, when we purchase the Turtlebot robot, we run the software, we run the setup there, and we connect our bot to the network. It'll be the exact same. So that's the good thing about ROS. It's modular. So in this example, we managed to simulate actual hardware using a simulation. And that's really one of the good things that I know about ROS. So why we use simulator, second of all, because if you purchase your own robot, Turtlebot, it will be $1,000 per person. So doesn't make sense for a learning start point to purchase an expensive robot. So of course, if you're interested in learning more, do install Gazebo, to install ROS, the full desktop version one, and you can try run with Gazebo simulations because that's the best way to learn. So yeah, I guess that's all from me. Now we have a photo session. So if you want to join the photo session, please turn on your camera. Anyone interested in joining? Oops, where's my view?
Actually, please join, guys, because this is for MLDA documentation. Yeah, but if you feel uncomfortable or you don't have camera, then it's fine.
Okay, I'll be taking the photo in 1, 2, 3. Okay, I think that's good enough. And before we end the workshop, there's one more thing that I need your help with, and that's to fill up this feedback form. I'll put the link in chat. And yeah, that's all from me. Thank you for attending, and yeah, have a nice weekend.